So hello guys, today I'm going to teach you a problem of the Stokes theorem. So here we go. First we need to understand what the Stokes theorem means. So first we know that to calculate the current we can do it by the closed integral of the electric field uh, by the dot product of a differential line. Also, we know that we can calculate our current using a double integral. So we have to calculate first the curl. So the Stoke theorems. So in this exercise, we're going to evaluate both sides of the Stoke theorem. For this example, we have given the electric field H equals to 7r power 3 cosine of theta in the phi direction. It's obviously is amperes over meters divided by 0 to pi in the phi axis. In theta is from 0 to pi over 6, and the radio is going to be 0.25. So for this exercise we need to evaluate the Stokes theorem. First we're going to try our the left side of our equation. So the differential line of spheric coordinates, we can search it in Wikipedia, and we found that is this. But we are only going to use this value because due that it's dot product, it's only possible to do the dot product between these two because they have the same direction. So we are going to have the integral of 7r power 4 cosine of theta sine of theta in the phi direction. and since it's in the phi direction, we can consider all this as a constant. So we take out the constants of the integral and remember the limits that the problem told us before. So we have to replace those limits in these variables. So we got that r is 0.25 and theta is p over 6, and we also get we have to evaluate the integral from 0 to pi in the phi direction. Once we solve these equations, we are going to get that our current is of 0.074 amperes. Now we have to do the right side to prove and to see that it is okay. So our right side, first we need to get the differential surface. In this case, due that our r is a constant, we use this one, this differential surface in the r direction. So first we need to calculate the curve. We can use this equation to calculate the curve. Okay, so we have to notice that since the equation of our electric field only has the h5 component, we only have to use it. We don't have to use all. So our equation is going to be like this. We only use this from all the big equation, because the other values are going to be 0, since there are no variables or not other directions in the vector. So uh, we replace h5 in our equation, and we're going to get this, that it's 1 over r sine of theta that multiplies all of this in the r direction, plus 1 over r that multiplies all of this in the theta directions. So the the curve is going to give us this, but since our differential surface is only in the r directions, this is the only term that we are going to use, this one. So here, as I told you, since our differential surface is in the r directions, our dot product is only going to be this by this. So first we do our dot product, and it's going to be 7r powered 4 cosine of 2 theta, the differential of theta, differential of phi. Now once we calculate the curve, and we do the dot product, we now can evaluate the integral. So we have to remember the limits that the problem told us before, and the only thing you have to do is replace the variables in each value. So here we have that since r is constant, we can we can take it out from the integral, also the 7. So our integral is going to be 7r powered 4, a double integral of cosine 2 theta d theta d phi from 0 to pi over 6 and from 0 to 2 pi. So if we solve this, our current is going to be also 0.074 amperes. So we have proven that we can solve either using a differential surface or a differential line. So we have proven the Stokes theorem for this exercise. Thanks for all, and thank you for watching.